Yesterday was Mental Health Day, so I hope you got a good rest. So we'll continue with chapter number 8, confidence intervals. We have looked at so far two situations or two cases. First one is when sigma is known, second one sigma not known. And today let me go over case 3, confidence interval for proportions. Suppose that insurance companies did do a survey. They randomly surveyed 400 drivers and found that 320 claimed they always buckle up. We are interested in population proportion of drivers who claim they always buckle up. So A, B, C, D, E are related to this situation. So first one is we need X. How many claimed they buckle up? So that number is 320. We need sample size. So how many drivers were asked? So that was 400. And then how much is the proportion? So 320 over 400. So 4 over 5 is 80%. 0.8. Part B, define the random variable X and P in words. Random variable X is number of drivers who claim they buckle up. And proportion, so we have to put this in words. So that's the difference between X and P. P is the proportion, X is simply the number. Part C, which distribution should we use for this problem? If I make a picture of this, it's going to look like this. Average proportion is 0.8, and we have to figure out standard deviation of P, which is square root of P times 1 minus P over N. So 0.8 times 0.2 over 400. So that should come to 0.02. Sigma of P that we are going to use is 0.02. We can say P follows normal distribution with mean 0.8 and standard deviation 0.02. Construct 95% confidence interval. 95% confidence interval for population proportion P. So this is what we use. So with this we can go to POSIT Cloud. In chapter 8 we are using library BSDA, and every time you open this session again, you may have to run this library so that it is active, and then we can use this formula that we have been using. So I'm just going to copy this towards the bottom and paste, and this is problem 115D. So mean we said is 0.8 for the normal distribution. Standard deviation was 0.02. So I'm just using these numbers. So 0.02, sample size was 400 drivers. Confidence level we want is 95%, so we have to say 0.95. And that's it. So 0.79 to 0.801. So 798,802 if you round this to the nearest decimal. So I used 0.8 sigma 0.02 and confidence level. So each one of these lines end with comma. So we use this in R and got confidence interval as 0.798 up to 0.802. So although in the sample 80% of the drivers indicated they buckle up, in the population you would expect about 79.8% to 80.02%. So very narrow confidence interval. One last thing that in this chapter is quite useful is figuring out sample size. If you are conducting a study and you want to figure out how much sample should I take. If you are doing it for a company, for example, and you want to test something in a company where it is expensive, like how many items you can test is expensive. When you go to the manager may say that we only have this much budget and you cannot do more than this. So there should be some way of figuring out like how much sample size for a given situation I really need, so that when I go and ask for funds, I'm able to like convince my boss or whoever is funding. Whatever number that we get using these calculations are theoretical numbers, like statistical numbers. I cannot go and say I need 1,000. Each item costs like, let's say $500. So a company may not be ready to spend that much money just because I want very accurate confidence intervals. But having some idea how much sample I should go for, so at least that should be there in the mind, and then you can work around that. So one situation is when you have sample size n for continuous random variables. And to derive this n, what we do is we make use of case 1, where you have confidence interval like this, x bar plus minus z alpha by 2 sigma over square root of n. In this one, this part is called, now how do I figure out how much sample size should I have? So for that I should know how much accurate confidence interval I want. So if this plus minus term is smaller, your confidence interval is more compact. And if margin of error is big, then your confidence interval is very wide. So you don't want very wide confidence intervals. You want something which is more accurate. So you can fix that first and say that I want this plus minus term, margin of error, to be 5% or 3%, and then do a back calculation and figure out what can be sample size that will give me that. So suppose we name this margin of error as, if we label this as E, so E equals z alpha by 2 sigma over square root of n. And then we can solve for n and we get a formula for sample size. So if you square both sides and take n on the left side, what we get is n equals, so z alpha by 2, sigma will remain this side because I'm shifting n to the left, E will come down, and then because we have squared this whole thing, so square. So this will give us a sample size for a given confidence level that we want, a given plus minus term that we want, and we have to assume some sigma. Because we have not collected any sample yet, so we don't have estimate of sample standard deviation, so we have to assume some sigma here. So that is one situation, and in R you can use n size function and supply these values like E, sigma, and confidence, and also mention type equals within quotes mu, like which calculation you are doing. So that also will use this formula and give you sample size. So that is one area where n is continuous random variable. Second situation is when we are interested in sample size n for binary random variables. So once again, binary, we know we are talking about p, and the formula is p plus minus z alpha by 2, and then square root of p times 1 minus p over n, where this part is called margin of error, or E. And if you do the same thing with this formula, you get a sample size formula for proportions. E equals z alpha by 2, p times 1 minus p over n square root. Square both sides, bring n to the left, you will be left with, so z alpha by 2 and E, so these will get squared times p times 1 minus p. So once you find z alpha by 2, you can use even a calculator to figure out what is sample size that will be needed. If you are using R, the function is n size. We provide E, we provide P, we provide confidence. And this time for type, we say within quotes PI. So this is in R. Example 8.9. Mobile phone company wants to determine percentage of customers who would upgrade to the latest version of smartphone from their current smartphone. How many customers should the company survey in order to be 90% confident that estimated proportion is within 3 percentage points of the true population proportion of customers who will upgrade? You can see they have worked out this problem. And when you are calculating sample size needed, if you have 751 point anything, 0.2, 0.7, 0.9, whatever you have, you should always round up. So 752 will be the sample size that will give whatever they want to get. In this formula, you also have P, but that problem doesn't say anywhere what should be P. So if P is not given, because anyway survey has not been done, so how do you know what will be the proportion? So we come to know about how many customers will like to upgrade their smartphone only after collecting data. How do we know before? We have no idea. So what we assume is, we assume a proportion of 50%, because that's the worst case scenario. So if you have 50%, that will give you the maximum sample size, and anything less than or more than 50% will give you a smaller sample size. So what is recommended here is you go with P of 0.5 if it is not given, so that your sample size at least is the maximum possible. We'll make use of this information that is given. E is given as 0.03. Confidence that we are interested in is 90%, and P is not given. So I will use this function n size and provide 0.03, P 0.5. I'm just using that box. and confidence level 0.9 and type equals PI. So let's go to R. So this is example number 8.9. I'm going to run this library so that you don't miss. We always need this one to solve these problems. BSDA. Anything that for which you have a question in your mind, if you have a function in R, you are not sure what it means and what should I provide. So you can put that question mark here and type, I want to know more about this n size thing. So n size. So if you run that, your fourth window will become help window and give you all the details. N size, then you need B. B is the design bound, that plus minus term. Sigma, what is P, what is confidence, and so on. N size, it says the first thing it needs is the bound B. So B equals 0.03. P equals, because it's not given, so by default I'm using 0.5. Confidence level is 0.9 and type, when you hover your mouse there, it only accepts MU or PI. So this one is proportion, so we'll use PI within quotes. So that gives you 752. So sample size needed will be 752. So I told you if I use P of 0.5, that will give me maximum sample size. So since we have this here, what if P is only 0.4? So you can see sample size comes down. Or if P is 0.1, sample size comes down to 271. Same thing on the higher side, so 0.8 for example. Sample size is 481. So when you have this number at 0.5, you get maximum sample size, 752. 752. Okay, let's look at one situation where there are two confidence intervals. So let's call this 1 and this is 2. So one is narrow, other is wide. Now if we have one of them is, let's say, 90% confidence interval, another one is 95% confidence interval. So my question is, which one is this, A or B? Basically what we are looking at is, if we increase the confidence level from 90% to 95%, what will happen to the confidence band? Will it become narrow like the first one or wide like the second one? Which one is the second one, A or B? If you would consider that if we increase the confidence level and it becomes wider, then your answer will be 95. If you say if you increase the confidence level, it becomes narrower, then your answer is 90%. Which one do you think is this wider one? Explain your thinking. I will give you one example. Wait, let's say this chair. So if you weigh this chair, give me an estimate like what it is likely to be in pounds. What is likely to be the weight of this chair? Obviously, based on your experience in lifting things, you may have some rough estimate. I'm not looking for like exact number, but some rough number. 2 pounds? Okay, so that's what is our point estimate. It's based on a guess, but that's a point estimate, one number. And we are 100% sure that it cannot be exactly 2 pounds. It may be slightly more, slightly less. So what range will you give? Plus minus something? So now we have a confidence interval. Whatever may be the level of confidence, but we have a confidence interval that it could be anywhere from 1.5 pounds to 2.5 pounds. Let me give you a challenge. Like if I bring a weighing balance, and if the weight is not between 1.5 and 2.5, you'll have to pay me $1,000. But I will allow you to change your interval so that you don't lose any money. So what will be your new interval? How much?
Can I keep it the same?
Oh, so you are so confident. How do you know?
I don't.
So you are ready to lose $1,000? So you want to play safe. What will happen to this interval? Will it become narrower or wider? So if I say 0 to 100 pounds, if I give a very wide interval, the chances of me losing any money is almost gone. Here there is still some chance, like it could be 2.51 or 2.52 or maybe 3 pounds. Who knows? Like it's quite heavy. So, but here we know that it cannot be more than 100 pounds. And obviously it cannot be 0. So what we did was we increased our confidence level, but what happened to the interval? It became wider. With more confidence level, the interval became much wider than original one. If you come back to this situation, which group is correct? 95% group made the correct choice, because when you increase the confidence interval, it has to become wider. So all these people have to take a transfer to second group. Second one was the right group. So it always happens that if you want a wider confidence interval, your confidence band expands. And to emphasize that further, what we'll do is, in a group of 2 or 3 people, you'll be asking 10 other people in the class how many hours they studied. You collect that data, calculate 90%, 95%, and 99% confidence interval, and then also figure out if you want to be within plus minus 3 hours, what will be the sample size needed. So you are combining 2 things into one in this exercise. So please take one. You calculated 90, 95%, and 99% confidence intervals for population mean. This is one of the examples where 90% confidence interval was from 2.1 hours to 4.9. 95% was 1.78 to 5.23. And 99% was 1.02 up to 5.98 hours. So clearly you can see as confidence levels increase, like from 90 to 95, 95 to 99%, this range increases. So it is more compact for 90, wider for 95%, and widest in this example for 99% confidence interval. So basically your conclusion is that as you increase confidence level, confidence interval becomes wider and wider. So if somebody has 99.9999% confidence, it doesn't mean that you have a very accurate number, because your confidence interval may look like anything from almost 0 to 100. which can become meaningless.